When I was in college, I had a friend teach me how to juggle, kind of like this. Now, I'm not a great juggler. I can usually keep 3 up in the air, but I can't do a lot of fancy tricks or anything. But one thing I learned about juggling is the most important characteristic is to throw the ball consistently at the same height. And so if you watch me when I juggle, when I'm doing it well, the balls are always going about the same height. And when I'm not doing it well, then one's going really high and one's going lower, and it's throwing me off. So it turns out that this consistency really matters. And when it comes to the world of statistics, it's hard to measure things like consistency. So today what we're going to talk about is the most important measure of consistency, and that is the standard deviation. But to start, let's just watch myself juggle a little bit in slow motion. So I have this ruler behind me, and I'm going to juggle in front of the ruler, and we're going to see how high the ball goes and how consistent I am as I juggle. Here we are zoomed in so we can see it a little better. Our first ball hits at around 19 3/4. Our second ball is around 20 1/4. Our third ball is around 20 1/2. Our fourth ball here is about 21 1/4, and our last one is right around 19. So here are the 5 numbers we just found, and to visualize these numbers to see how spread out they are, we're going to place them on a number line. So I'm going to place each of these on a number line, so 17.95 goes here, and then we'll just place all the others on the number line as well. Now, if we want to talk about how spread out something is, we need to talk about how far it is from the center, and the most natural way to define the center is the average. So let's real quickly calculate the average, and we'll get an average of mu equal to 20.15. But let's mark that average here on the number line. And now we get some picture of how spread out our dots are, because each dot is a certain distance from that line. So the next thing I want to calculate is how far is each number specifically from the line itself. So for example, this number 19.75 is this far from the line. And I would just simply subtract the 2, and I would do 19.75. And I would subtract 20.15, and when I do that, I get negative 0.4. And that tells me that 19.75 is 0.4 units to the left of the center. And I'll do this for all of my values. And instead of talking about it really slow, let's just speed up and do this a little quicker. So there we go. We found the distance between each point and the center line. And so these distances here are in some ways giving us our first glimpse of how spread out the data is. Notice if these distances are really large, then we have really spread out data. And if they're small, then our data is less spread out. So let's come over here where I have them written a little bit better. Now what we probably would like to do would be to average these distances. But you know there's a bit of an issue here because we don't want this positive number and this negative number to cancel each other out. So what we need to do is we need to make all of our distances positive. And the logical thing would be to use absolute values. And that's a pretty reasonable way to tackle the problem. But it turns out that's not the way we're going to tackle it. We're instead going to square the distance. And so I'm going to take this negative 0.4 and square it. And what I'm going to get is 0.16. And so that's going to be that first square distance. And I'm going to go through and I'm going to square all the others. There you go. So now that we've squared them all, we've made all of our numbers positive, and then we can look over here, and if we look at our squared numbers and see how big they are, then they're giving us a picture of how far each of our points are from that center value. So why do we square them and not just make them all positive? Well, I'm not going to go into great detail, but the heart of it lies with the Pythagorean theorem. You'll remember the Pythagorean theorem. It's if we have an A and a B, and then we want to find some distance between these 2 points C, we use A squared plus B squared to get C squared. And so it turns out distances behave really nicely with these squaring properties. Well, it turns out this is true also in 3 dimensions. If it's a 3-dimensional shape, then you have to do A squared plus B squared plus C squared equals D squared, and then you have that 3rd dimension. And it turns out this is a great way of measuring distance in all dimensions. So what we're really doing when we're squaring these is we're doing kind of a Pythagorean theorem type calculation to put all these together. So here we are, we found the points, we found the distance between the point and the center of all of our data, and then we've squared those distances. Now all we want to do is take an average of these distances. So that means we're going to start by summing all of these together. And I'll let you do that on your own, but know that the answer is 2.825. And then once we have that sum, we simply find the average. And so the average is that sum divided by 5, which in this case is 0.565. And so this is a good measurement of of how spread out our value is. This is called the variance of the value. Notice this variance doesn't actually tell us how spread out the distances are, but how spread out the squared differences are. So we've averaged those squares differences. So to get our standard deviation, all we want to do is we want to take the square root of that variance. And so if we take the square root of that variance, we get 0.751665. So a quick summary of the standard deviation. There are two ways of thinking about it, but they're both equivalent to each other. The first is thinking of the standard deviation as an algorithm, and this was the algorithm I just described. So when we have a bunch of data, we start by finding the average. That was that middle point on all of our data points. Then we find the difference between each point and the average. Once we have each of those differences, we square them, average the squared differences, and then take a square root of the result, and that gives us our standard deviation. I have a fancy math formula for you, which some of you I know like math formulas, and this will be great. If you're overwhelmed by this math formula, no problem. The algorithm says everything that the math formula does. But here's the formula. We can see sigma, which is the letter we're going to use for standard deviation, is, you'll see this x minus mu. This is the value that we're given minus the average. So that's the distance between the point and the average. We're going to square that difference. And then this big sigma means that we're going to sum all of those. And so we take those differences, add them together, divide by n, and take the square root. So if you like this, if you like formulas, this is a pretty good formula to go with. Now let's come back to our original number line and see what our standard deviation is telling us about how spread out these values are. Remember, our standard deviation was 0.751665. So let's move from this center point that we had, and let's move over 0.75 and see what we get. So remember, this was about 20.15. So move over 0.75 and we're at almost 21. So this is one standard deviation from the mean as we've moved from here to here. Similarly, if we move to the left 0.75, we'll end up somewhere right around here. So you'll notice something interesting about our standard deviation. It doesn't cover all of our data values, but it covers most of them. See, 3 of them are inside, and the 2 that are on the outside aren't very far away. In fact, they're close enough that if we were to add one more standard deviation on both sides, we would have captured all of our points. So if we move over 2 standard deviations, we've captured all of our points. And so this is a general principle. The general principle is that within 1 standard deviation, we get most of our points, and most usually being about 2/3 of our point. Within 2 standard deviations, we get almost all of our points. So you're not guaranteed to have all of them, but by the time you have 2 standard deviations, you have almost all of them. Usually about 95% is a reasonable standard. And 3 standard deviations, you really have all except for the most extreme outliers. So the standard deviation ends up being a pretty good measurement for us to tell us where our data is. So once we have our standard deviation and we have the center point, we have a pretty good picture of where most of our data, where almost all of our data is, and we have a picture of what makes something an extreme outlier. So if it ends up being more than 3 standard deviations away, then we think, oh man, that's an outlier. Maybe we should consider whether that's a number we want to throw out or not. There's one last thing to think about, and that is thinking about the sample instead of a population. Technically, this whole problem was a sample standard deviation, but I calculated the population standard deviation because it's a little simpler mathematically. The sample standard deviation is a very similar idea. The only difference in the sample is instead of dividing by n when we go through the problem, we divide by n minus 1. And the only reason for this is when you're using a sample instead of a population, the sample has a little bit of bias, and we as statisticians have found out that when we use n minus 1 instead of n, we get a better approximation of the standard deviation, the population standard deviation using the sample standard deviation. When we switch to sample, we use an S instead of a sigma, and when we switch to sample, we usually use X bar instead of mu, although those are the exact same numbers. So sample standard deviation is done the exact same way, except here when I did average, instead of dividing by 5, I would have divided by 4 if it was a sample standard deviation. Well there, now that we know a little bit about calculating standard deviation, I want you to recognize just how important this calculation is going to be for the rest of the semester. You see, mostly in statistics, what we want to do is compare our sample values with our population values. And if we have a sample where the standard deviation is fairly low, that is, the values within our sample are all pretty consistent, then we can be pretty confident that our sample is going to do a good job resembling or giving us information about our population. However, if the standard deviation is really large, we have big swings and big changes from one data value to the next, then we have much less confidence in what's going on in our population. And that's actually what the rest of the semester is going to be about. It's about how do we use what we know about the data, including the standard deviation, to make good conclusions about the entire population. So with that, we'll practice calculating some standard deviations in class, and I'll see you then.